The landscape is vast, desolate, and frozen. This is the Mongolian steppe in deep winter. The temperature is minus 40 degrees Celsius. The wind is a physical force, a constant, brutal pressure with nothing to stop it for thousands of kilometers. In this environment, survival is measured in minutes. And yet, people live here. Not in concrete bunkers or subterranean shelters, but in this, a small, round structure made of felt and wood. It looks like a tent. It weighs less than a small car and can be packed onto 2 camels. Our modern intuition screams that this is impossible. How can a lightweight, portable dwelling withstand conditions that would challenge a modern building? This isn't a story about ancient magic. It's a story about a level of engineering so sophisticated it looks like simplicity. To fully grasp the scale of this engineering challenge, we need to understand a specific Mongolian word, zud. It's a term for a winter disaster, a perfect storm of environmental horrors. It can mean extreme, prolonged cold, heavy snow that buries the grazing lands, or freezing rain that encases the grass in a layer of impenetrable ice. For nomadic herders, the zud is an existential threat, capable of wiping out entire herds and endangering human life. In these conditions, a shelter isn't a matter of comfort, it's the line between life and death. Now, look again at the gur. From the outside, it appears to be the opposite of what this environment demands. Our modern architectural logic, shaped by centuries of settled life, tells us that a strong building is a heavy one. It has deep foundations, thick, rigid walls of brick or concrete, and a massive frame to resist force. The gur has none of these. It is, in essence, a collapsible wooden lattice, a few roof poles, and layers of felt, all held together by tension and rope. It sits directly on the frozen ground. To an uninformed eye, it seems impossibly fragile, a temporary shelter completely outmatched by the lethal embrace of the steppe. This forces us to ask a fundamental question. Is our definition of a strong or warm structure incomplete? Have we, in our pursuit of permanence and mass, overlooked a different kind of resilience? Researchers of vernacular architecture note that the gur isn't just surviving in spite of its design, it's surviving because of it. But before we can even begin to understand how this structure retains heat, we have to address a more immediate, violent threat. In a place with no natural windbreaks, where the wind is a constant, crushing force, the first challenge isn't staying warm. It's avoiding being torn to pieces. The first secret of the gur isn't about heat, it's about pressure. To see how the gur deals with this pressure, we must first look at its most obvious feature, its shape. A square building meets the wind like a wall. It creates a zone of immense pressure on one side and a vacuum of chaotic, destructive turbulence on the other. This is what rips roofs off and pulls structures apart. The gur, however, is round. Traditional builders learned over millennia that a circular form offers no flat surface for the wind to push against. Instead, the wind flows smoothly around it, much like air over an airplane's fuselage. The force is distributed evenly across the entire structure, drastically reducing the peak stress on any single point. But the real genius is in the roof. Its low, conical shape is not an aesthetic choice. It's a crucial aerodynamic tool. As wind travels up and over the gentle slope, it creates a subtle zone of lower pressure above the gur. More importantly, the angle of the roof deflects the wind upwards. In a principle of physics that modern engineers would recognize, this upward deflection of air creates an equal and opposite downward force, effectively pushing the gur more firmly onto the frozen ground. In the moments of the strongest gusts, the gur becomes more stable, not less. This aerodynamic elegance is paired with a brilliant structural system. The wooden frame, the collapsible lattice wall known as the kana, and the roof poles called uni, is not designed for perfect rigidity, it's designed to flex. Held together by tension and rope, the entire structure can absorb and dissipate the energy of a sudden gust by deforming slightly, like a willow in a storm, before returning to its shape. A rigid structure would shatter, the gur yields. So the gur doesn't fight the wind, it harmonizes with it. It survives the pressure. But surviving the gale force winds is only half the battle. Once the wind passes, the deadly, silent cold remains. The Gur's wooden skeleton and aerodynamic shape can't stop heat from escaping into a -40-degree night. For that, we need to look at its skin. The skin of the Gur is not a simple covering. It's a sophisticated, multi-layered thermal system. The critical component is the turga, thick blankets of dense, pressed wool felt. On a microscopic level, this felt is a masterpiece of natural engineering. The matted wool fibers trap millions of tiny pockets of still air. And as thermal science confirms, still air is one of the most effective insulators known. It's this trapped air that creates the primary barrier against the brutal cold, preventing the warmth inside from escaping. But insulation alone isn't enough. Researchers of vernacular architecture point to a second, equally vital property: breathability. Inside the Gur, people breathe, cook, and live, releasing a constant stream of water vapor into the air. In a modern, sealed structure, this moisture would condense on the cold inner walls, soaking the insulation and then freezing solid, rendering it useless. The Gur's felt layers, however, are designed to breathe. They actively wick this moisture from the warm interior towards the cold, dry exterior, allowing it to pass through the wall and dissipate. Much like high-performance outdoor clothing, the system keeps the interior dry and the insulation effective. This system is built in layers: a thin cotton lining for the interior, followed by 1 to 3 layers of thick felt, depending on the season and the wealth of the family. Finally, an outer layer of waterproof canvas protects the felt from rain and snow. At the center of this insulated, breathable shell sits the stove. It is the thermal heart of the Gur, the engine that constantly pumps heat into the space. With this thick, breathable insulation and a powerful central stove, the Gur can effectively contain warmth. But this solution creates a new, silent, and potentially deadly problem: suffocation from smoke and carbon monoxide. A perfectly sealed home with a fire burning inside is not a shelter, it is a trap. The Gur's final piece of engineering genius turns this lethal problem into the very key to its comfort and livability. The solution to this life-or-death puzzle of fire and air is found at the very peak of the structure, the circular opening at the roof's apex, known as the tonneau. To a modern eye, a hole in the roof seems like a critical flaw, a point of weakness. In the Gur, it is the linchpin of the entire climate system. Its most obvious function is as a chimney, allowing smoke from the central stove to exit safely and directly. But its true genius lies in how it drives ventilation. The hot air from the stove naturally rises. As it escapes through the tonneau, it creates a subtle, low-pressure system inside the Gur. This, in turn, gently pulls colder, denser, oxygen-rich air into the dwelling from the small gaps under the door and the base of the walls. This incoming fresh air is then drawn directly towards the central stove, where it is heated, rises, and continues the cycle. The result is a constant, gentle convection current, a slow thermal engine that circulates the air. This system does 3 things at once. It continuously replenishes the oxygen supply, prevents the buildup of smoke and carbon monoxide, and distributes heat with remarkable efficiency throughout the circular space, leaving no cold corners. The design helps ensure that the very act of heating the Gur also keeps its air fresh and breathable. Even the door is part of this system. It is traditionally low, forcing a person to stoop, which minimizes the amount of cold air that rushes in when it's opened. And its placement is not random. It almost always faces south or southeast, turning its back to the prevailing northern winds and opening itself to the low winter sun for a small but crucial dose of passive solar heating. We have seen how the Gur defeats the wind, traps the heat, and even breathes. Every component, from its shape to its materials to its openings, is a clever piece of a puzzle. But when you step back and see the whole picture, you realize this isn't just a collection of survival tricks. It represents a fundamentally different philosophy of what a home is and how it should relate to the world around it. We have taken the Gur apart, piece by piece. We've seen how its circular form blunts the wind, how its felt skin breathes while insulating, and how a simple opening in the roof drives a sophisticated system of heat and air. But to see these as separate solutions is to miss the essential truth. The Gur is not a collection of clever features. It is a single, integrated system, a design perfected over countless generations of iterative development. This is a masterclass in nomadic engineering, where every element is optimized for multiple functions. The wooden frame provides structure but also critical flexibility. The felt provides warmth but also vital moisture control. The roof opening is a chimney, a ventilator, a source of light, and for a culture that lived by the sky, a clock and a calendar. In this design philosophy, there is no waste. It stands in stark contrast to much of our settled architecture, which often relies on brute force, tons of concrete and steel, and massive energy inputs to fight the environment. The Ger does not declare war on the steppe, it achieves a state of equilibrium with it. This principle is embodied in its very substance. Built almost entirely from renewable local resources, wool from the herd and wood from the sparse forests, the Ger has an incredibly light environmental footprint, and at the heart of its design is the core requirement of nomadic life: portability. The entire home can be dismantled in a few hours, packed onto a handful of animals, and leave little more than a faint circle on the ground. It is the ultimate expression of architecture that is both deeply rooted in place and yet completely untethered. So we must return to our initial question. We saw a simple-looking structure and wondered how it could be so resilient. But the story of the Ger suggests we were asking the wrong question. The real question is, what is advanced technology? Is it the machine that consumes the most resources, or the one that achieves the most with the least? The Ger is not a primitive artifact. It is a timeless solution, a testament to a design philosophy that remains profoundly relevant, reminding us that sometimes the most resilient structures aren't the heaviest or the most rigid, but the ones that have learned to be light, flexible, and intelligent.